There is a category of target that is more dangerous than any missile battery, more consequential than any hardened command post, and more difficult to justify striking because its existence is measured not in warheads or launch rails, but in the absence of something, the absence of communication, the absence of situational awareness, the absence of the coordinated response that separates a functional military force from a collection of individual units operating in mutual ignorance of each other's position, status, and intent. Electronic warfare infrastructure is that category of target. It does not project force. It erases the ability to project force coherently. And the facility that the Iranian military had constructed beneath a ridgeline in the East Azerbaijan province, 31 kilometers southeast of Tabriz, was the most sophisticated example of that category that the intelligence community had ever built a target folder against. The facility was not a jamming station in the conventional sense. What had been built beneath the Tabriz ridgeline over 11 years was a signals exploitation and denial complex, a facility that received, processed, and characterized every electromagnetic emission in the Iranian airspace battlespace and used that characterization to generate precision electronic warfare effects against specific targets at specific moments. Its output had been present in the collection record for 4 years in the form of anomalous jamming events that could not be attributed to any known Iranian platform, and that demonstrated a knowledge of American communication architecture so specific that the signals intelligence analysts had begun describing them not as jamming, but as electronic intelligence, the product of a system making decisions about what interference to generate, when, against which frequencies, in response to which observed operational activities, with the goal of creating specific gaps in adversaries' situational awareness at moments when those gaps were most consequential. The gap it had created 3 months before the targeting decision was the event that converted the facility from a high-priority intelligence target to an active strike requirement. The gap had occurred during a time-critical operation in the theater, an operation whose details will not be specified, and its effect had been to deny a specific element of the operational force, the communication architecture, it required to execute a time-sensitive task at the moment the task was time-sensitive. The denial lasted 11 minutes. 11 minutes was not catastrophic in absolute terms. In the specific operational context of the denied communication, 11 minutes was enough. The after-action assessment of the event produced a targeting recommendation. The targeting recommendation produced a decision. The decision produced a target folder that had been growing for 4 years and that was now, for the first time, complete enough to support execution. The facility's physical architecture had been designed by engineers who understood that an electronic warfare complex presents a specific detection vulnerability that a ballistic missile production line or a centrifuge hall does not. It has to transmit. A facility that transmits can be found by the signals it generates, regardless of how deeply it is buried or how carefully its surface signature is managed. The designers had addressed this vulnerability with a technical solution that had added 2 years to the facility's construction timeline, and that had been, for those 2 years, the single most expensive line item in its budget. A fiber-optic transmission infrastructure that connected the underground facility's antenna arrays to surface emission points distributed across a 12-kilometer radius around the facility's actual location. The emission points looked, from any collection angle, like the surface infrastructure of a civilian telecommunications network. Relay stations, repeater housings, junction boxes installed on existing utility corridors whose electromagnetic signatures were consistent with their cover purpose. The facility's actual transmissions emerge from these distributed surface points rather than from any antenna associated with the underground complex. A signals intelligence analyst looking for the source of the anomalous jamming events was not looking for a facility. The analyst was looking for a network, and the network was indistinguishable from infrastructure that had a legitimate reason to exist. The intelligence that defeated the deception came from a source whose operational details will remain undescribed, who provided a technical document specifying the fiber-optic routing architecture, the underground facility's coordinates, and the depth and layout of the hardened chambers. The document was authenticated by cross-referencing its content against the signals collection record. The emission point locations in the document match the geographic distribution of anomalous jamming events plotted over 4 years of collection. The network the analysts had been studying for 4 years was in the document. The facility behind it was in the document. The folder was complete. The depth was the mission's central problem. The Tabriz facility's chambers sat at a depth exceeding the GBU-57's design penetration capability in the volcanic basalt substrate of the East Azerbaijan highlands, harder than the limestone and granite formations of previous targets. The weapons engineers addressed the shortfall through a fusing algorithm modification that transformed the weapon from a penetration system into a seismic one. Rather than attempting to breach the chambers directly, the modified algorithm detonated each weapon at maximum achievable basalt penetration depth and relied on transmitted seismic energy to compromise the chambers structurally. 2 weapons, same aim point, 17 seconds apart, the first establishing a fracture pattern in the rock above the chambers, the second driving energy into that fracture pattern at a frequency computed to maximize resonant loading on the chamber walls and ceiling. The engineers assessed the probability of achieving required structural compromise at 87%. The 13% was documented. The decision was made. 17 seconds between 2 weapons at the same aim point required 2 aircraft flying parallel headings at a precisely computed airspeed differential, a differential that placed them at release position 17 seconds apart. The margin for error was plus or minus 4 knots over an 11-hour flight profile. The mission commander of the lead aircraft tracked the differential from departure. He made 11 corrections over 11 hours. The largest was 3.2 knots. The window was maintained. The 2 B-2 Spirits lifted off at 8:44 p.m. and 8:51 p.m. from the forward location, climbing into broken overcast that closed above them within 4 minutes of departure and reduced the visual environment to the instruments and the glow of the cockpit displays. The overcast was forecast and had been built into the route planning as a favorable condition. The cloud layer that reduced the pilot's external visual reference also reduced the thermal contrast environment that the infrared detection systems of any ground observer would use against the aircraft. The aircraft were already above it by the time it mattered. They climbed to altitude and separated to the lateral spacing the coordination geometry required, the spacing that, combined with the airspeed differential, would produce the 17-second impact interval over the Tabriz ridgeline 11 hours and 19 minutes from now. The first tanker contact occurred at 1:52 a.m. The trail aircraft's contact followed at 2:07 a.m. The coordination geometry required both aircraft to complete their contacts within a 12-minute window to maintain the airspeed differential's validity over the remaining flight. They completed within 13 minutes. The 1-minute overrun was within the planning margin. The lead aircraft's mission commander noted it in his tracking log and made the airspeed adjustment that restored the differential to within the 4-knot window. The adjustment took 40 seconds. He confirmed the restoration and continued his monitoring rotation. At 6:31 a.m. local time, as the two aircraft entered the outer coverage range of the northwestern Iranian air defense network, the EW package that had been assembled for the penetration phase activated against the defense architecture, covering the approach corridors to the Tabriz region. The northwestern sector of Iran's IADS was oriented primarily toward the Turkish and Azerbaijani borders, the directions from which a NATO or Gulf transiting threat would approach. It was layered with S-300 systems at the strategic level and a combination of medium-range acquisition radars and TOR-M1 point defense batteries in the inner ring, all networked into the national IADS architecture through fiber-optic data links that the anomalous jamming events of the preceding 4 years had been generated through. The facility beneath the ridgeline had been using the national network's own communication infrastructure as its transmission medium. Destroying the facility would not merely eliminate its EW capability. It would remove a component from the national IADS architecture that the network's operational managers believed was a passive relay rather than an active intelligence and denial system. The network's managers did not know what they were managing. The target folder knew. The distinction was operationally significant in the aftermath planning, not in the execution. The EW package that the Growler flights provided against the northwestern approach sector activated at 6:31 a.m. and encountered the defense network in a state that the pre-mission signals intelligence assessment had not fully characterized. The Tabriz air defense sector had, in the preceding 72 hours, conducted a scheduled readiness exercise that had resulted in 2 additional TOR-M1 batteries being repositioned from their garrison locations to field positions that the exercise design had designated as operationally representative. The exercise had ended. The batteries had not yet returned to garrison. They were in field positions that the pre-mission imagery had not captured because the imagery collection that fed the target folder had been completed before the exercise began. 2 additional TOR-M1 batteries in uncharacterized positions meant 2 additional fire control radars that the Growler EW officers did not have specific frequency suppression allocations for. The lead Growler's passive receiver detected the first uncharacterized TOR-M1 emission at 6:34 a.m., 3 minutes after the jamming package activated. The system characterized the emission, matched it to the TOR-M1's known emission profile, geolocated it to a position that was not in the pre-mission database, and presented the EW officer with a new threat symbol on his situational display. He had a suppression allocation protocol for this contingency, a general-purpose reserve allocation that could be applied to uncharacterized TOR-M1 emissions, and he applied it within 8 seconds. The first uncharacterized battery's picture degraded. The second appeared on his display 11 seconds after the first, geolocated to a different position, also not in the database. He applied the same reserve allocation to the second battery. The reserve allocation was now fully committed to 2 uncharacterized targets. He had no remaining reserve. If a third uncharacterized emission appeared, he would need to reduce coverage on one of the pre-planned allocations to generate capacity for a response. He reported the situation to the Mission Coordination Data Link and continued. No third uncharacterized emission appeared. The 2 field-positioned batteries operated in partially suppressed states throughout the penetration phase. Not fully jammed, not fully functional, their fire control pictures showing the specific quality of degradation that experienced operators learned to recognize as jamming rather than equipment fault. But that does not, in a heavily contested electromagnetic environment, produce the crisp, unambiguous evidence that supports an engagement decision. The operators of both batteries reported jamming. Neither reported a valid contact. Neither engaged. The B-2S entered the target area approach corridor at 7:08 a.m. The coordination geometry that had been maintained throughout the 11-hour flight was intact. The airspeed differential was within 2.8 knots of its design value. The lateral separation was within 40 meters of the computed requirement, and the timing projection that the lead aircraft's mission commander had been tracking since departure showed the second weapon's predicted impact time at 17.3 seconds after the first. The margin against the design requirement was 0.3 of a second. 11 hours of monitoring, 11 corrections, and a 1-minute overrun at the tanker contact had produced a 0.3 of a second residual. He noted it. He did not consider it significant. He continued. The pre-release phase produced the mission's most acute threat exposure at 7:14 a.m., when the S-300 battery, positioned on the high ground north of the Tabriz plain, the battery whose coverage geometry the approach routing had been designed to minimize, activated its fire control radar in a mode that the B-2's passive warning receiver characterized as not a scheduled acquisition sweep, but an off-cycle activation, a specific radar operating mode that the emission library associated with a queuing event rather than routine search activity. Something had queued the battery. Not the B-2. The aircraft was outside the S-300's detection range at the current geometry for a non-cooperative target at its radar cross-section profile. Something else had queued it. The mission commander ran the queuing scenarios in the time available. The Growler's jamming suppression on the S-300's acquisition radar was active. The battery was operating on a queuing input from somewhere in the sensor network, possibly the partially suppressed Tor-M1 batteries, possibly the early warning radar layer, possibly a source that the collection had not identified. He did not know the source. He knew the S-300's fire control radar was active and that the aircraft was at the boundary of its detection range, and that the detection range for a target of interest that the battery had been queued toward was different from the detection range for a non-cooperative target the battery was passively scanning for. Queued searches are more sensitive. He was at the boundary of an unqueued detection range, and he did not know how far inside a queued detection range he was. He transmitted the priority code to the Growler flight that allocated maximum output to the S-300's fire control frequency band. The Growler's EW officer received the code and redirected power from the two partially suppressed Tor-M1 batteries to the S-300 fire control radar. The two uncharacterized Tor-M1 batteries, no longer suppressed, operated on clear frequencies for 42 seconds. In those 42 seconds, neither produced a valid contact on the B-2S. The S-300's fire control radar, under maximum Growler suppression, swept 3 times without generating a return above its detection threshold. At 7:15 a.m. and 19 seconds, the battery's fire control radar returned to standby mode. The off-cycle activation was over. The queuing event, whatever had generated it, had not produced a contact. The Growler EW officer restored partial suppression to the two Tor-M1 batteries. The aircraft continued. At 7:19 a.m., the lead aircraft reached its initial point. The pre-release checks completed in the compressed sequence that the terminal phase required. The targeting system confirmed the GPS solution against the subsurface aim point, the coordinates that existed in the technical document provided by the intelligence source, at a position beneath the basalt ridgeline that no onboard sensor could independently verify, at a depth the weapon could not directly reach, but whose structural response to the modified seismic employment solution the engineers had modeled at 87% confidence. The bay doors opened. The first GBU-57 released. The aircraft corrected the departure pitch and turned onto its post-release heading. The bay doors closed. The clock started. The trail aircraft's mission commander was watching his own clock. The countdown that represented the 17-second interval, the coordination geometry had been designed to produce. At weapon separation plus 9 seconds, he was at his initial point. At weapon separation plus 14 seconds, his pre-release checks were complete and the targeting solution was confirmed. At weapon separation plus 15 seconds, his bay doors were opening. At weapon separation plus 17 seconds, the second GBU-57 released from the forward station. The interval between the two weapons' impacts, computed from the aircraft's GPS positions, and the weapon's computed flight times, was 17.1 seconds. The design requirement was 17 seconds. The residual was 1/10 of a second. The first weapon struck the basalt formation above the chambers at 7:19 a.m. and 53 seconds. Its penetration proceeded to the maximum achievable depth in the basalt substrate, a depth that fell short of the chambers by a margin that was precisely the margin the engineers had modeled when they designed the seismic employment solution. The detonation at that depth drove a seismic energy pulse into the basalt that the structural analysis had characterized as the initiation phase of the resonant loading sequence. The fracture pattern that the detonation established in the rock above the chambers was not visible, not audible, and not felt at the surface. It was present in the rock. The second weapon arrived at 7:20 a.m. and 10 seconds, 17.1 seconds after the first. It followed the penetration channel created by the first weapon into the fracture zone and detonated at a depth that the modified fusing algorithm placed inside the established fracture pattern rather than at the surface of undamaged rock. The second detonation drove energy into the fracture network at a frequency and magnitude that the structural analysis had computed would maximize the transmitted loading on the chamber walls. The resonant effect was not a single pressure event. It was a mechanical sequence, a series of stress cycles transmitted through the fractured basalt that accumulated damage in the chamber structure faster than the structure's material properties could absorb it. The chamber ceiling failed at 7:20 a.m. and 14 seconds, 4 seconds after the second detonation. The failure was partial, not a collapse, but a fracture network that propagated across the ceiling's lateral extent and produced a structural condition that the engineers had defined as the threshold of irreversible compromise. The signals exploitation equipment in the primary chamber, the servers, the processing arrays, the signal characterization systems, the fiber-optic routing hardware that connected the underground facility to its distributed emission network across the 12-kilometer surface radius, experienced a structural loading event that their installation specifications had not been designed to survive. They did not survive it. The seismic signature reached the surface monitoring station at the East Azerbaijan Provincial Geological Survey Office at 7:20 a.m. as a 2.1 magnitude event, small, localized, at a depth and with a waveform that the duty seismologist logged as unusual in its sharpness, but consistent with the microseismic activity that the local fault system generated intermittently. He noted it in the event log. He would revise the note 4 hours later when a second look at the waveform showed characteristics inconsistent with natural seismic events and consistent with underground explosive employment. He filed a formal report. The report's distribution included elements of the Iranian government that would spend the following hours determining what had happened and whether the 2.1 magnitude event was the entirety of the story or the surface evidence of something more consequential. It was more consequential. The facility's surface infrastructure, the fiber-optic relay stations, the repeater housings, The junction boxes distributed across the 12-kilometer radius continued to function after the underground complex was eliminated. They functioned as exactly what their cover purpose said they were: telecommunications infrastructure, transmitting nothing, connected by fiber-optic lines to a facility that was no longer processing anything to transmit. The network remained. The brain behind it was gone. The anomalous jamming events that had defined 4 years of collection would not recur. The two B-2s completed their post-strike egress and reached the tanker rendezvous at 10:47 a.m. The transfers completed without incident. Both aircraft turned west. The data links carried confirmation codes. The planners who received the codes ran the seismic data that the monitoring network had been collecting since 7:20 a.m. and confirmed the event signature. They cross-referenced the signature against the structural model's predicted output for a successful resonant loading sequence. The correspondence was within the model's stated uncertainty band. The 87% had been the outcome. The 13% had not. The numbers that closed the package: 11 hours and 19 minutes of flight time. 2 GBU-57 massive ordnance penetrators, employed at a 17.1 second interval against a single aim point in a resonant seismic sequence. 4-knot airspeed differential maintained across 11 hours with 11 corrections to produce a 17.1 second impact interval against a 17-second design requirement. 2 uncharacterized TOR-M 1 batteries in unplanned field positions, managed with reserve EW allocation that left no further margin. 1 S-300 off-cycle activation generated by an unidentified queue addressed with maximum Growler output and 42 seconds of degraded TOR-M1 suppression. 0 contacts generated by any Iranian system. 0 aircraft lost. 1 underground electronic warfare complex eliminated at a depth that direct penetration could not reach through a seismic employment sequence that had never been used in combat and that the engineers had assessed at 87% confidence. The 13% did not arrive. Electronic warfare is invisible by design. It operates in the electromagnetic spectrum. It produces its effects without physical manifestation, and it leaves no debris at the point where it is applied. A facility designed to conduct it is the most difficult category of military infrastructure to find, to characterize, and to eliminate, because its existence is proved not by what it is, but by what it does. What the Tabriz facility did, across 4 years of collection, was leave a pattern in the electromagnetic record that was precise enough to locate it, characterize it, and ultimately remove it from the spectrum it had been shaping. The pattern it left was more information than its designers intended to provide. It was enough. The ridgeline above Tabriz looks unchanged. The spectrum below it sounds different.